Okay, so today we will look at one of the most recent chemistry papers, October-November 2022, paper 61. Okay, let's take a look. Okay, so for question 1, we have this experimental setup here. Let's take a look. Okay, so it is given that sulfur dioxide gas is toxic. It is denser than air and soluble in water. Sulfur dioxide gas can be made by adding dilute hydrochloric acid to sodium sulfide and heating the mixture. Yeah, so essentially we have sodium sulfide here. Sodium sulfide, the solid here. And then we have hydrochloric acid. Okay. So when we mix together, it will produce the sulfur dioxide gas. The gas made can be dried by passing through concentrated sulfuric acid. Okay, passing through concentrated sulfuric acid. So we have the concentrated sulfuric acid here. So yeah, so the gas will be produced here, passing through the tube. Okay, reaching the concentrated sulfuric acid and then dried by the sulfuric acid and then collected here. So here we have the apparatus set up by the student to collect the sulfur dioxide gas. There are 2 errors in the way the apparatus has been set up. We will discuss about this shortly. Let's start with the first question. First question, indicate with an arrow on the diagram where the heat should be supplied. So we should heat up the experimental setup. Where should we do it? Okay, it should be right here, directly under the conical flask, the heating. Straightforward. Second question, give the name of the apparatus label A. A here, very straightforward. This is a conical flask, no problem. Next question, name of the substance labeled B. This part is also straightforward. We have the sodium sulfide solid here and then adding the hydrochloric acid. Sodium sulfide there. Next, why this experiment should be carried out in a fume cupboard? Okay, so we already know that sulfur dioxide gas is a toxic gas. So we should do the experiment in the fume cupboard. So the fume cupboard is going to have the exhaust to collect the toxic gas. Okay, so it will be safer. Next question, identify 2 errors in the way the apparatus has been set up. Okay, so what are the 2 errors? First one, the tube linking flask should go into sulfuric acid. Okay. The second one, the glass jar should not be inverted. Okay. Another one, tube from flask to gas jar should not go into acid. Okay. Yeah. Yeah. So the first error here, this tube, it should go into the acid. Okay, because we make sure that all the bubbles of the gas that form here will pass through the acid and getting dried there. Okay, so this is the first error. The tube should go into the acid. And then this tube, it should not go into the acid. Okay, it should not go into the acid. We need to make sure the gas pass through the acid and then comes out and then go into the tube. Okay, so if the tube is inside the acid, then is not effective to collect the gas. Okay. Yeah. So another thing, because we are given that the sulfur dioxide is denser than air. Okay. So when it comes out here, it will go down because it's denser than air. So the correct setup, it should be like this. Okay. So it should not be inverted. So it should be like this. Okay. So we will collect the gas. Here, it is denser than air, so we can collect the gas effectively. If we use the inverted gas jar, then the gas, it will go down because it is denser than air. So these are the two errors of the setup. All right. Next question. Okay. So here we have a student investigated how the solubility of sodium sulfate in water changes with temperature. Okay. So even before we start, we know that in general, solubility will increase when temperature increase. Okay, we are familiar with that. All right, eight experiments were done. Okay, so we will take a look at the details. Firstly, mass of empty evaporating basin was found. So we will take evaporating dish and then we will weigh it. Okay. So we will weigh the evaporating dish. And then excess sodium sulfate placed in the beaker. So we have sodium sulfate placed in the beaker. 100 cm cube of cold water added to the beaker. Okay, so added the water. The mixture in the beaker was stirred and heated until it has reached a temperature of 15 degrees Celsius. Heated until 15 degrees Celsius. Some of the sodium sulfate had dissolved to form a saturated solution. And then 25 cm cube portion of the saturated solution removed from the beaker and transferred to the evaporating basin. The evaporating basin was heated until no more steam could be seen and solid sodium sulfate remained in the evaporating basin. The mass of the evaporating basin and the solid sodium sulfate remaining was found. So essentially, we find out at 15 degrees Celsius, the maximum amount of the sodium sulfate dissolved. And then what do? We take 25 cm cube and then we place onto the evaporating dish. Okay. And then we heat it up. Okay. So we take the evaporating dish and then we heat it up until all the water is gone. All the water is gone. We left the sodium sulfate there. Okay. So this one is the one that was dissolved just now. Okay. Yeah. So this is how we find out at 15 degrees Celsius how many grams of the sodium sulfate dissolved at 15 degrees Celsius. Okay. And then experiment 2, 3, 4, 5, 6, 7, and 8. We are doing exactly the same thing. Okay. Exactly the same thing except with higher temperature. Okay. So all we are changing in this experiment will be the temperature. So we know the temperature will be the independent variable in this case, and the amount dissolved. How much of the sodium sulfate dissolved will be the dependent variable. Okay. And we know that in general, when temperature increase, the solubility will also increase. So in this experiment, we will confirm that. Okay. So here we are given a table that record all of the information that we have. Okay. So we can see the headings, very straightforward. So first column, we just label all of the experiments. We have experiment 1 to 8, no problem. And then for the second and third column, we have the independent variable. So independent variable, which is the temperature. Okay. So we are controlling the temperature. So here, the practice here is for reading the thermometer. So this part should be very straightforward. Okay. So here, 22, no problem. 29, 32, and then 34, 46, 61, and 84. So we are increasing the temperature for each experiment. Okay. And then the remaining 3 columns will be related to the dependent variable. Okay. Related to the dependent variable. Dependent variable is about mass of solid. Okay. So the mass that has been dissolved. Okay. So how do we find out the mass that has been dissolved? So first, we have the empty evaporating dish, and then we have the evaporating dish that has the sodium sulfate. Okay, so straightforward. How do we find out? Okay, so let's say this is A, this is B. So how do we find out the mass of the sodium sulfate? Mass of the sodium sulfate will be B minus A. So the evaporating dish with the sodium sulfate minus the empty evaporating dish, straightforward. Yeah, so we can do this for all of them. For example, the first one, 58.1 minus 54.2, so that will give us 3.9. So this is how we find out the mass that has been dissolved. So we can do the same for all of them. Okay. Yeah. And then according to our expectation, okay, we can see that as we increase the temperature, okay, the solubility increases. Okay. But when we go from 46, 61, 84, we can see that it's almost constant. Okay, so it decreased a little bit and then it is almost constant. Okay, yeah. So basically, we can see that there is a limit, okay, to the solubility. So at some point, it will become constant. All right. So next part of the question, we're going to plot the results from experiment 1 to 8. So we are supposed to draw 2 curves of best fit, one through the first 4 points and one through the second 4 points. Extend the 2 curves so that they cross. Okay. So we have mass of sodium solid sulfate remaining, okay, which is this column here, okay? So we should plot this column, which is the dependent variable. And then for the temperature here, we should plot this column here, which is the independent variable, okay? So we will plot one by one. Okay, so we will do that quickly. Okay, for the first point is 15 degrees Celsius at 3.9. Okay, 15 degrees Celsius, 3.9, somewhere around here. Okay, and then second point, 22, 5.9. 22, 5.9. Okay, next point, 29, 9.6. 29, 9.6. Next, 32, 11.7. 32, 11.7. Okay. And then next, 34, 12.3. Okay. 34, 12.3. Okay, hold on. All right. 46, 11.7. Okay. 46, 11.7. Okay. 61, 11.2. 61, 11.2. 84, 10.8. 84, 10.8. Okay. Yeah. So we supposed to draw the line of best fit for the first 4 points and the last 4 points. Okay. Okay. So line of best fit. Okay. Something like this. And then, okay. And then we should identify the point where they cross. Okay, so which is somewhere here. Hold on. Okay. So it is 32. And then here this is 12.4. Okay. All right. So we'll look at the next question. From the graph, deduce the mass of solid sodium sulfate remain in the evaporating dish when the mixture in the beaker is heated to 55 degrees Celsius. Okay. Yeah. So basically, when we plot the graph, it is quite useful because we can use the plot to predict other situations. Okay. So for example, we didn't do the experiment at 55, but we can use the plot to predict what should happen at 55. Okay. So, okay. At 55. Okay. So 55 degrees Celsius. Okay. All right. So it crosses at this point. Okay. So around this point here. Okay. So this is 11 here. So this is 11.2. Okay. So we expect at 55 degrees Celsius, the solubility will be around 11.2. Okay. Yeah. So if we look at the marking scheme, exactly the case. That's what we expected. Okay. So any answers between 11.2 and 11.4 will be acceptable. And our answer is 11.2 in this case. Okay, no problem. Next question. The mass of sodium sulfate remaining in C1 is the mass of sodium sulfate that dissolved in 25 cm cube of solution at 55 degrees Celsius. Use your answer in C1 to calculate the concentration in gram per dm cube of saturated aqueous sodium sulfate at 55 degrees Celsius. Okay, so we know that, okay, for our situation, we have at 55 degrees. Okay, so just now we find out at 55 degrees, we have 11.2 grams dissolved in 25 cm cube of the solution. Okay, so because at first we dissolve in excess, okay, of the water, and then we pipette out 25 cm cube to put into the evaporating dish, and then we evaporate the water. So essentially, we are working out the solubility in 25 cm cube of water. So here, the solubility that we have is 11.2 grams in 25 cm cube of water. Okay, but in general, for our result to be comparable, we always convert to a standard concentration, so we can compare easily with other experiments. So here, we need to convert to gram per dm cube. Okay, so yeah, so basically 11.2 is already the correct unit, no problem. We don't need to do anything. So now the cm cube, we need to convert to dm cube. Okay, so we know 1 dm cube equals to 1000 cm cube. So this we can rewrite in two ways. Okay, so if we move 1000 to here, we get 1 dm cube over 1000 cm cube equals to 1. Okay, or on the other hand, if we move 1 dm cube to here, we have 1000, we have 1000 cm cube over 1 dm cube equals to 1. Okay, so these are the two conversion factors that we can use. Okay, so we're going to choose this one. Okay, because this one, the cm cube is on top. Okay, so we'll see shortly. 1000 cm cube per 1 dm cube. Okay, so this can be quite handy because now we can cross out the cm cube. So that's why we choose this one. For this one, we can cross out the cm cube. So we cancel the unit that we don't want. We are left with the unit that we want. Okay, so this is very useful. Okay, so now we can straight away see what we need to do. 11.2 multiply 1000 divided 25, giving us the unit that we want. Okay, gram per dm cube. So that will give us the answer 452. Hold on. Let me calculate. Okay. 11.2 multiply 1000 divided by 25. 11.2 multiply 1000 divided 25. Okay, so that gives us 448. 448 grams per dm cube. Okay, so that's the idea for this question. Okay, next. Okay, student repeated the experiment and found 11 grams of sodium sulfate remain in the evaporating basin. Okay, use your graph to deduce two possible temperatures to which the mixture in the beaker that may have been heated. Okay, this is the other way round. So just now we are given the temperature. We want to find the solubility. Okay, so this is the other situation whereby we are given how much is dissolved. We are given the solubility. We need to find the temperature. At which temperature this amount will be dissolved. Okay, so what do we do? Okay, yeah, so essentially we will draw a line at 11. Okay, on. Okay, so we'll draw a line at 11. Okay, so we will see where it crosses. So we can see that it crosses the plot at these 2 points here. Okay, these 2 points. Okay, and somewhere here. Okay, okay, so somewhere around here. So if we take the reading, we will get around around 31. Okay, 30.5, around 31 here. Okay, and then here it is around 67. Okay, yeah. So this will be our answers. Okay, so at 31 degrees Celsius and 67 degrees Celsius. Okay, take a look. Okay, and the marking scheme. Okay, so the two temperatures at 11 grams, 31 and 67. Okay, so that's the idea. Okay, name an item of an apparatus that can be used to remove 25 cm³ portion of saturated solution from the beaker. Okay, so here we need to measure exact volume, okay, of a solution. So when we want to remove exact volume, the most suitable apparatus will be the pipette. Okay, so the pipette will allow us to measure exact volume, okay, accurately. Suggest why. Okay, suggest why it is important to excess sulfate is added to the water in the beaker. Okay, so at the start of the experiment, we will add the sodium sulfate. We make sure that it is in excess, and then we add the water. Okay, yeah. We make sure that it is in excess so that we have more than enough, because we want to find out the solubility at different temperature. Okay, so when the temperature increase, the solubility is increased. So we need to make sure that after we increase the temperature, we still have enough sodium sulfate to dissolve. Okay, yeah, so that's the main point. To ensure we can form a saturated solution so that not all dissolve. We want something remain, making sure that we have enough to dissolve in all of the water. Okay, suggest why the mixture in the beaker was stirred as it was heated. Okay, so as we are heating it, we will stir it. Okay, straightforward. To speed up dissolving. Okay, all right, next question. So the saturated solution. So once we done the dissolving, we will pipette out 25 cm³ to put in the evaporating dish. Okay, and then what we do, we will heat up until no more steam could be seen. Okay, yeah, we want to make sure we remove all of the water. Suggest a better way of ensuring all of the water has been evaporated. So now what we do is we check visually, okay, whether any more steam is produced, okay, but that is not that accurate. So we may still have some water remain in the solid. So the better way to do this will be reheat and reweigh, okay? So basically we heat to a certain extent, we will weigh it, okay, on the balance, okay? We have a certain reading, and then we heat again, and then we check the reading again. We keep heating until the mass stop changing. So when the mass stop changing means all of the water has been removed. Okay. Next, use your graph in B to deduce what would be observed if a saturated solution of sodium sulfate is cooled from 80 to 50 degree Celsius. Okay, so we can take a look. 80 to 50. Okay. So 80 to 50. So we are interested So we are interested about this part here. Hold on. Okay. So we are interested about what happens, okay, between 80 and 50, okay? So the solubility of 80 is here, which is around 10.8, okay? So 80 is around 10.8, the solubility, okay? At 50 is around here, which is 11.3, okay? So we can see that going from 80 degrees Celsius to 50 degrees Celsius, the solubility decrease. Okay? Yeah. So normally, when we increase the temperature, the solubility will increase, but this is the other way around. Okay? So going from 50 degrees Celsius, 80 to 50, we have solubility increases from 10.8 to 11.3. So solubility increase. Okay. So when we cool it down, normally when we cool down something, okay, for example, let's say between 20 and 30. Okay. So between 20 and 30, when we cool down, the solubility decreases. When the solubility decreases, what happens? It will crystallize. Okay. We will get the solid crystallized out. Okay. Normally. But because this case, when we cool down the mixture from 80 to 50, the solubility increase. If the solubility increase, we don't have anything crystallized out. So in this case, we expect no change. Okay, so we don't observe anything changing. So the answer will be no change, remain colorless. Okay, so that's the main idea for this question. Okay, next. Okay, question 3. Normally, we will have identification of cations and anions. Okay, so here we are given two solids, W and X. Okay, so we start with W. So W, we are given the identity. Okay, so we are given the identity. So we should know the test results, okay, for this situation. Okay, so test on solid W, complete the expected observations. Solid W dissolve in water to form solution. So first we take this solid and then dissolve in water, okay, and then divide it into 3 equal portions, okay. So 3 equal portions. To test the first portion, we add aqueous ammonia and then dropwise and then in excess. Okay. So first is test 1 is ammonia, dropwise and then to excess. We know that ammonia is a test for cation. So here we are testing about the zinc. Okay. So we need to recall when we add ammonia to zinc, what is the expected observation? Okay. So for this, we can refer to the identification of the cation table, straightforward. When we have zinc, when we add the dropwise, first we will get white precipitate. When we add in excess, it will dissolve. Okay, what we expect for the zinc bromide. So the second portion, we will add nitric acid and barium nitrate. Okay. So nitric acid and barium nitrate. So we know this is a test for sulfate. Okay. So this is a test for sulfate. So here we do not have sulfate. So for this test, we expect no change, okay? No reaction happen. And then the third portion, we add dilute nitric acid and then silver nitrate, okay? This is straightforward. We know this is a test for halide, okay? Chloride, bromide, iodide. If we have chloride, we will be white precipitate, bromide, green precipitate, iodide, yellow precipitate. So here we have bromide. Very straightforward. We expect to have green precipitate. Okay, no problem. Moving on to the next question. So here the solid X is unknown. Solid X is unknown. So we are running some tests here. Okay. So we can yeah, so based on the test result, we can have some information. Okay. What do we do? 1 gram of solid X placed in the boiling tube and heated strongly. A strip of filter paper soaked in acidified aqueous potassium manganate solution was held at the mouth of the boiling tube. Okay, so acidified potassium manganate turned from purple to colorless. Okay, so this shows that the potassium manganate, it is reduced. Okay, so means this solid X here, okay, it is oxidized. Okay, so oxidized. Okay, so what happened here is we have SO2 gas produced. Okay, so for this test, essentially we test for the presence of SO3 or SO4. Okay, so one of these could be present. So this is the first result. Okay, then test 2, we add dilute nitric acid and then silver nitrate. Okay, so again, we know this is test for halide. Okay, so no change, nothing changed. So means halide is not present in this sample. Okay, next, dilute nitric acid and then barium nitrate. Okay, so this one, we know this is a test for the sulfate. Okay, white precipitate form. Okay, white precipitate form means sulfate is present. Okay. Next, aqueous sodium hydroxide added in dropwise and then excess green precipitate. Okay. So sodium hydroxide, when we get green precipitate, it will be iron 2 plus. Okay. So with this, we have all of the information. Okay. Gas given off in test 1. So we know for this test, we will produce SO2 gas. So the answer will be SO2. Okay. Water vapor also given off in test 1. Chemical test for water. Okay. So chemical test, we have 2 tests that we can use for the presence of water. Okay, so the first one is cobalt chloride. Okay. Cobalt chloride, if water is present, it will turn from blue to pink. Another test we can do is copper sulfate. If water is present, it will turn from white to blue. Okay. So finally, we can identify solid X. Okay. So we already know it is iron sulfate. Okay. So iron sulfate. All right. Okay. Last question. Okay. So normally for question 4, we need to design the experiment. Okay. Take a look. Leaves of some trees contain colored substances which can be used as pH indicators. Okay. So essentially, what we want to do, we have the leaves. Okay. Okay. So inside the leaves, we have some substance. Okay. We need to extract. Okay. So essentially, we are doing extraction here. Okay. So the leaf itself, it is a solid. Okay. So we need to have some so this substance here, okay, it could be water soluble, okay, or it could be soluble in alcohol. Okay, so what we do here, we will process the leaf with alcohol so that the substance that we want will dissolve in alcohol. Then we will filter or with another method to separate the solid part, then we can have the substance in the alcohol. So that's the main point. Okay. So we have three colored substance, okay, that are soluble in ethanol but insoluble in water. Okay, so here we are given it is soluble in ethanol. So we will use ethanol to extract these substances. Assume that nothing else in the leaf soluble in ethanol. Okay. Yeah. So basically, we will plan an investigation to extract the colored substance from the leaves and then see if they work as a pH indicator. Okay. Yeah. So first, we have the extraction. Secondly, we will test with the test solutions. Okay. So yeah, for example, we can use acid. We can test the substance in acid and the alkali. So acid, for example, we can use HCl. Alkali, for example, we can use sodium hydroxide. Okay, so if we test this substance in the acid and then in the alkali, if it shows a color change, then it means it can work as a pH indicator. Okay, so we are provided with the list from the tree and common laboratory apparatus and chemicals. Okay, so we can think about what are the steps that we can use for this extraction. Okay, straightforward. So first, we will crush and grind the leaves. Okay, so we will use mortar and pestle. So we put the leaves there, grinding. Okay, grind into small pieces. Okay, this is very useful because it will increase the surface area for the extraction, and then it will also like break the cell wall, okay, and the cell membrane, break the cell wall and cell membrane. So the substance that we want can be um extracted easily. So using mortar and pestle. So by mentioning mortar and pestle, we can get 1 point as well. So we add the ethanol. So the ethanol is added. Okay. So now the substance can dissolve. And then we filter. Okay. When we filter, we can separate. Okay. So when we filter, okay, so the leaves will be collected at the funnel, and then the alcohol with the colored substance will be collected. Okay. And then we separate into two portion. Okay. And then one of them we will add acid. For example, we can add HCl. And then the other one we will add the alkali. Okay. For example, sodium hydroxide. Okay. And then if there is color change, means these can act as pH indicator. So that's the main idea for this question here. Okay. Yeah. So up to this point, the paper is done.